Okay, so we have a problem to sort out with the Poisson distribution in that we now want to find the expected value of a Poisson random variable and, of course, the expected value of x squared and consequently the variance of the Poisson random variable. Before we do that, we will do a little bit of playing around with the Taylor series for e to the lambda. So we have a standard result that k is 0 to infinity, the sum of lambda to the k over k factorial is e to the lambda. So the first thing I'm going to do, because I guess we know where we're going with this, is to differentiate both sides of that with respect to lambda. So of course the right hand side we know just gives e to the lambda, but it's the left hand side that's interesting. We obviously going to end up with k multiplied by lambda to the power k minus 1 divided by k factorial. And just a little note, we can start this sum at k equals 1 because for the first term in the series, if k is 0, the first term is 0. So the next thing we're going to do, because I don't like powers to the k minus 1, is multiply both sides by lambda. So that will give us instead what I think is a much tidier k multiplied by lambda to the k divided by k factorial, and that now equals lambda e to the lambda. So that was kind of interesting, and we're just going to repeat the process. So first thing we did, to differentiate both sides with respect to lambda, and if we do that again, we end up with one of those unpleasant looking k to the minus 1s. So we now have k squared multiplied by lambda to the k minus 1 divided by k factorial, and this of course now equals e to the lambda plus lambda e to the lambda. A little bit more work differentiating lambda e to the lambda. Now, again, I want to get rid of that lambda to the power k minus 1, so I'm going to multiply both sides by lambda. So if I do that on the left-hand side, I end up with a sum that is taken over all values of k from 1 to infinity of k squared multiplied by lambda to the k divided by k factorial, and with a little bit of tidying, rearranging, we're going to end up with something like e to the lambda multiplied by lambda plus 1 multiplied by another lambda. So just a little bit of playing around and a little bit of manipulating, because we're going to find that those patterns are the very patterns that crop up when we're finding the expected value of x. So by definition, the expected value of x is the sum of the value of a realization of a random variable multiplied by its probability mass function. And pretty much as we did when checking the Poisson was a valid PMF, we can pull out the e to the minus lambda because that sum is constant with respect to that term is constant with respect to the k we're summing over. And now we should be able to recognise that we have already done the little manipulation, and we've found that the term on the right part of that equation is e to the lambda. So we have e to the minus lambda, lambda e to the lambda. And that, of course, tells us the expected value of x is lambda. So we want to find the variance. So the first step in finding the variance is to find the expected value of x squared. And again, how do we find that? We want to find the sum over all values of k of g of k, p of k. And if we do that, we have an expression that looks similar to the one we've had before. So the first thing we're going to do is remove e to the minus lambda, which is constant for the sum. And then we end up with a term that should look familiar from our other manipulations. The sum of k squared, lambda to the k divided by k factorial. We recognise that and fill in the details. E to the minus lambda, e to the lambda, lambda plus 1 multiplied by lambda. So of course that tells us the expected value of x squared is just lambda plus 1 multiplied by lambda. So last thing I want to do is to find the variance of x, which is the expected value of x squared minus the expected value of x all squared. And plugging in the values we found, this is going to be lambda 1 plus lambda minus lambda all squared, which is lambda plus lambda squared minus a lambda squared, and that leaves us at the very end minus lambda squared, so that leaves us at the very end just with a lambda. So the interesting feature here of the Poisson distribution is that the expected value of x is lambda and the variance of x is equal to lambda.